Sabi dito, it is an idealized thermodynamic cycle that describes the workings of a constant pressure heat engine. Pagdating sa Brayton cycle, marami rin mga pangalan ang involved. Una na nga dyan, si John Erickson, kung saan nabanggit niya natin sa Erickson cycle na the first heat engine cycle na imbento niya ay ang tinatawag ngayon na closed Brayton cycle. Ganun din, since maraming contribution when it comes to the concept of Brayton cycle, kaya siya ni-name after George Bailey Brayton. And meron pang involved dyan. Okay, so si John Barber naman. So hindi ko na nalagay dito, no? Okay, si John Barber yung kauna na nag-patent ng first engine cycle no using the Brayton cycle. Though dahil nga maraming ang contribution si Brayton, sa kanya pinangalan. Okay, kaya tinatawag rin siyang Joule cycle kasi nga si James Prescott Joule, siya rin yung nag-provide ng first theoretical description doon sa pagiging constant pressure cycle. Anyway, doon tayo sa tawag sa kanya, which is the Brayton cycle or the Joule cycle. Ang mga processes na involved sa Brayton cycle ay constant entropy, pressure, entropy, and another constant pressure process. Brayton cycle is usually used in the gas turbine. We have here two of the variants of a Brayton cycle. Closed Brayton cycle, open Brayton cycle. Makikita natin sa diagram na to ang difference ng dalawa. Sa closed Brayton cycle, meron tayong dalawang heat exchanger. While open Brayton cycle, meron lang siyang isa. Yun ay ang combustion chamber. For the simple Brayton cycle, makikita rin natin dito ang PV diagram at ang TS diagram ng isang ideal simple Brayton cycle. Mula point 1 papunta sa point 2, ang tawag natin dito ay isentropic compression, kung saan meron tayong fresh air na papasok sa compressor para pataasin ang temperature and ang pressure. Mula point 2 to point 3, ang tawag natin dito ay isobaric heat addition. The compressed air proceeds into the combustion chamber, kung saan mag-mix ito with the fuel at constant pressure. Mula point 3 to point 4 naman, isentropic expansion ang tawag dito, wherein the high temperature gases enter the turbine, where they expand to produce the work. Then, point 4, pabalik sa point 1, that is isobaric heat rejection. The exhaust gases exit to the atmosphere, releasing heat to the surrounding. Pupunta naman tayo sa mga formula na ginagamit sa simple Brayton cycle. Makikita natin sa TS diagram ang mga state points na gagamitin natin. So, be aware sa mga ito. Una, sa part na ito, dito natin i-compute ang heat added. At ang formula niya is MCP T3 minus temperature 2. Next naman, sa part na ito, nandyan ang heat rejected. And ito yung kanyang formula, MCP T4 minus T1. Next naman, sa part na ito, dyan naman natin kinocompute ang work ng turbine. Ay, the formula MCP T3 minus T4. And sa work ng turbine, certain part dyan ay dinadala natin dito. Dyan natin naman kinocompute ang work ng compressor. We have MCP T2 minus T1. meron tayong tinatawag na pressure ratio. Simply the ratio of the pressure sa outlet at inlet ng compressor. At nabanggit na rin natin kanina na part of the work ay binibigay natin doon sa compressor. At ang tawag naman natin doon ay back work ratio. So simply ratio ng compressor divided by the turbine work. For the Brayton cycle, by means of the pressure ratio, ito yung isentropic. Gagamitin natin ang pressure ratio sa isentropic. Ito yung kalalabasan. Temperature and pressure ratio. Okay? And another one, dun sa kabila, ito yan. So take note, ito ay para lang sa simple Brayton. Kung saan, ang pressure 1 is equal to 4, ang pressure 2 equals to pressure 3. That's why, ito yung kalalabasan. So since pareha sila ng right side, pwede natin equate yan. We will arrive for this formula. Same ng auto cycle kung babalikan natin. Ito yung relationship ng temperatures natin sa ideal, simple Brayton cycle. So yung mga formula natin involving yung mga state points sa Brayton cycle. Then, ito yung pinakamahalaga sa mga cycles. The thermal efficiency. Thermal efficiency, general formula that is work net over QA. Pero meron tayong mas mabilis na formula kung sakaling given ang pressure ratio. Ito yung formula natin. At ulitin lang natin, katulad kanina, yan ay applicable lang sa ideal, simple Brayton cycle. An ideal Brayton cycle operates between 15 psia, 60 degrees Fahrenheit, and 100 psia, 1,500 degrees Fahrenheit. The compressor and expander are both perfectly efficient. The thermal efficiency, net work, and back work ratio. First, we construct the TS diagram of the simple Brayton cycle. Then determine what are the given. Ay, makikita natin sa problem ang terms na ideal Brayton. Pag sinabi natin Brayton cycle, the type of substance is a gas. And for being an ideal, we consider it to be air. Although, kahit di man sabihin sa problem, ang default naman natin ay air, unless stated. Since that is air, we should be familiar with the value of K, which is in standard, that is 1.4. Then, 15 psia and 60 degrees Fahrenheit for 0.1. 100 psia and 1,500 degrees as 0.3. Tanong, bakit 0.1 at 0.3 ang designation natin? Okay, that is because the properties given refer to the minimum and the maximum points in the cycle. Since the ideal cycle has isobaric processes, pressures 4 equals pressure 1 and pressure 2 equals pressure 3. Ang required ay the thermal efficiency, net work, and back work ratio. We have two formulas for thermal efficiency. Either of the two will lead us to the same answer. Based sa problem, ang gagamitin natin ay ang simplified formula kasi mas mabilis ito kumpara dun sa isang formula. Okay, we still have the unknown value pressure ratio. Then we will substitute it to the original formula. We have now the answer efficiency equals to 0.4184 and multiply by 100% gives us 41.84%. Let's continue for the network. Our solution starts with the path function 1 to 2, isentropic process. Recall that in isentropic process, the relationship of temperatures and pressures is in this form. May we substitute the given to the formula. In the formula, temperature is in absolute. So we should add 460 for every arbitrary temperature. Now, we get the compressor outlet temperature to be 434.14 degrees Fahrenheit. Next, at temperature 4. Our solution starts with a process from 3 to 4. Again, another isentropic process. I simply change the subscript to 0.3 and 0.4. I substitute the given to the formula and we will get the answer 679.86 degrees Fahrenheit. Another way in solving the temperature 4 is by using this formula. Okay, we will arrive at the final answer, which is almost the same. My answer now is 679.87 degrees Fahrenheit. Let's continue for the network. The formula is, first substitute the compressor work. Next is the turbine work. Then the formula is using this formula. And we have 107.04 BTU per pound.